Uh, Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. It's Professor Hayoung Chung. He is an associate professor in the Department of Mechanical Engineering at UNIST in Korea. Before joining UNIST, he earned his PhD from Seoul National University in 2017, where he conducted research on spontaneous behaviors of thin smart strips. He subsequently worked as a postdoctoral researcher in Alicia's Kim group at UC San Diego, contributing to several topology optimization projects focusing on large deforming thermoelastic structures. His current research interests span multiple spatiotemporal scales in computational mechanics, including the multi-scale analysis of inelastic behavior in structures, topology optimization for large deformation structures, and the application of machine learning for accelerated modeling and analysis. He has received numerous government and industry research grants supporting advancements in areas such as 4D printing design platforms, data-driven multi-scale mechanics, and multi-scale mechanics of semiconductors. Young, thank you so much for joining us this week. And with this short introduction, you can start whenever you are ready.
Yep. Thank you for your introduction. Uh, I'd like to check if you can see the red dot here moving around. Is it okay?
Yes, yes, we can
Okay.
see it.
Okay, great. Good day, everyone. I know it's just right before lunch, so I'm not going to take tons of your time. And thank you for joining me for today's seminar. And my name is Hayoung Chung, as introduced, and I'm an assistant professor in the Department of Mechanical Engineering at UNIST in South Korea. And first, I'd like to express my deepest gratitude to Professor Kanyedakis and Dr. Uh, Toscano for inviting me to present our work. It's, uh, it's a great honor to share our research with such distinguished audiences. So today, I'll be introducing our approach, the called action PINN, which predict static equilibria in Landau phase transitions. But before I begin, I'd like to introduce a student of mine, Mr. Samin Lee, who executed most of the simulation results, is actually joining this seminar with me to answer your questions when it comes down to technical details. I especially want to credit him because today is actually the first day of our 1 week holiday celebrating Lunar New Year, and he's not able to go back to his home, although it's like 2 a.m. in Korea. Uh, I hope uh, so I hope it's worth it for him as well. So let me begin. So this is a roadmap of our today's talk, and we'll start with introduction, where we'll provide some of the background on my lab and my research focus. And then we'll move on to background, where I'm going to introduce some of the theoretical framework underpinning our work. And after that, based on the problems found in background, I'll present proposed methods. And later, the numerical result will be given to showcase how our work performs in different scenarios. And lastly, I'm going to give you a conclusion and some key takeaways. So let me begin. This is a brief introduction about myself and my lab. And personally, I've been studying solid mechanics over a decade, and starting with the multi-scale analysis, modeling with smart materials and nanomaterials, and then move on to nonlinear fine element of thin shells during my graduate studies in Seoul National University in Korea. And later, I started working on topology optimization during my postdoctoral degree research. And later, I move on to UNIST in South Korea, and I and my team member started working together since 2019, right before pandemic, actually. And since then, our primary research focus is on advancing solid mechanics through computational and AI-driven methodologies. So the main focuses are topology optimization of programmable materials and advancing data-driven and physics-constrained modeling to predict material behaviors, and of course, putting the material into cyberspace. And lastly, I'm also working on AI, integrating AI into the numerical simulations for faster and more accurate predictions. not in the way that the reduced order model, but I'm more working fascinated by the fact that AI itself can expedite the calculations of in when it comes down to numerical method like integrations. So our lab is a part of UNIST, which is a government-funded and research-oriented STEM university located in Ulsan. I don't think you know any of this, UNIST or Ulsan. So I'm going to give you a little bit of summary, brief introduction. So my university is relatively young and established 2019, but it has quickly grown to become one of the country's leading research institutions, like because it's one of the STEM university funded by Korea. And I have to say, is a little bit far from Seoul. Like it's like 2 hours, 2 hour on the fast train. And I doubt you know this place, right? So but I like to say this is unique location that aligns with our research. And this is our university and our logo and the time ranking or something. I'm not one of the particular liking it, but my university does. But anyway, the Ulsan itself is known for its robust industrial base, which includes shipbuilding, oil refining, and automotive manufacturing. And you might have seen like some of these companies like Hyundai or SK or Samsung, and Ulsan is actually where these companies were born and raised. And I particularly are intrigued by the fact that this industry environment serve as a source of inspiration, but most importantly, the industrial collaboration for much of our interest. And nonetheless, as I mentioned, I have my research interest is quite broad, but one of my research background concerns understanding and predicting the behaviors of the smart structures. Particularly, those are driven by some stimuli that is not pneumatic. I mean, for non-tactile stimuli such as light and heat. So the most prominent example structure is soft robot like this guy. And for example, and their actuations or their actuator, for example, hand like this guy, are typically manufactured by some smart materials like shape memory alloys or the liquid crystal elastomers that transversely moves back and forth depending on the stimulus is given. And those kind of behavior is usually governed by an intriguing phenomena called phase transition. This phenomena can be characterized by abrupt changes in material properties, like such as like stress state as an external condition is given, and external condition crosses some critical threshold. We like as a mathematicians or engineers altogether, of course, know such behavior for sure because it is widely known for water and polymer and superconductors. And I have to say, I guess no Korean will forget this word superconductor right after like 2024. But simply speaking, the modeling this phase transition behavior can be very straightforward. Say we know some like potential energies or free energy that are governed by some phases, like phase, and say here the liquid and the vapor. And each of these profiles is obviously convex, but in the view of system scale, there are a multitude of minima, such as or like infinite number of minima. As shown, the left, the summation of the energy is not strictly convex, and in the region, the water and vapor are like kind of mixed. So because it is the interim, and we say this phase is alternating in this region. The other example is a Landau model where also the multitude of stable equilibria points. So in all in all, this left the phase phenomena, change phenomena, like this governed by this guy is the first order phase transition, and for this case is called second order phase transition. But anyway, you can clearly see that predicting the phase transition uh, present two main challenges. The firstly is about discontinuities of the in free energy makes the numerical method unstable because numerical method really hate jumps or some discontinuities. And also the solution, the multiple stable solution can often exist. Maybe one solution is better than the other, but maybe the other, in some cases, the different solution may coexist. And it makes complicating predictions processes. And because of the nature of the PIN or neural network itself, it makes the regression more a little bit more smoother, and also can handle the optimization, doing the optimization and really non-convex profile. So we believe that PIN or some neural network method may offer solution to address these issues. That's what we motivate us to work on this project. So this is the background, and to better understand the phase transitions, we typically rely on Landau Ginzburg theory, which is devised by two well-known physicians. And this describes roughly the first and second order phase transition altogether, and introduce the order parameter to capture the degree in order in the material. And this case, the equation itself is modeling superconducting behavior, and you can clearly see that when temperature drops down to certain temperature, like Tc here, is the order of the system changes abruptly, and making the resistance to zero and making this kind of structure magnet gravitate. This is, of course, very complex in nature, but this model can be applied to more familiar system, like for the mechanical engineer like me, if as we take this quantum and electromagnetic terms out of it. Then it gets down to really the scalar value system that are governed only by the temperature change. Here, it is thermotropic. And in this case, as temperature change, the profile of the polynomial function gradually changes from convex to the non-convex case, as can clearly shown here. And as the temperature goes down, the optimum of the system, which was first black, is separated into several two different minima, or in some unsymmetric case, there are a multitude of the solution, but there are only one clear global minima. So you can clearly see that how the thing's getting complex, but still it is a polynomial. So we doubt whether this is really complex or not. But you have to think about it when it becomes like multiple dimensions or it combined with other complex energy profiles. It more complicates the non-convex energy landscapes, leading to solution multiplicity and also making solution like harder to converge. So the example that the system governed by such an energy is a liquid crystal. The order can can take a real value rather than the quantized integers. So we say this S is a scalar order parameter, and if it is one, when it's perfectly aligned, and it is a zero, it is completely isotropic. It can have some values in the intermediate values, so somewhat kind of mixed. So in this way, it model the liquid crystal's nature that has a property between liquid and solid. Their anisotropic behavior combines liquid flow and crystal alignment, making them essential for many advanced applications like sensor and responsive material, but most of all, like displays, because they have alignment as well. They can block the light depending on its stimuli. So the liquid crystal can be characterized by these two parameters, like one a scalar order parameter and vectorial alignment. And to capture their behavior more accurately, a tensor order parameter Q here is introduced to encode both alignment and symmetry and typically employed. And this Q tensor is symmetric, as you can clearly see, and traceless. And the behavior of liquid crystal is governed by several free energy components. So for example, this is the phase energy. So it's somewhat similar to the Landau energy. But there are also some energies that penalize, penalize the distortion of the structure of the liquid crystal, say the energy of distortion or Ericsson energy that penalize the distortion of the liquid crystal textures, and also it penalize the external distortions and anchoring energy, and of course minimizing energies provide insight into the equilibrium state of liquid crystals, as you can clearly see, because their energies are all combined and the mechanisms are conflicting one to the other. So obviously, the energy profile is non-convex and very complex. So it requires handling scalar parameter and directors in RP square in Lie group, and while navigating complex free energy landscapes. So here are the challenges. Firstly, it requires simultaneous handling of scalar order parameters as well as director orientations. And secondly, there are also physical or mathematical constraint that leaves the Q, the order parameter, on the specific Lie group. And lastly, we need a method that explores the free energy landscapes. Of course, there are many methods, including find element or find different method or the optimization for this matter. This analysis model is typically based on these two principles. The one, relaxation, is a traditional method to address this elasticity, suggested by John Ball. This is, I believe, he is a famous mathematician, and he introduced quasi-convexations to address this non-convexity. But there are also numerical approaches such as the phase field method or direct energy minimization driven by optimization. But as far as I know, they are still computationally intensive and sensitive to parameters. And from our experience, using this also necessitates the deep understanding of liquid crystal textures to conceive initial gases that are close to the real-world solution. So for the simulators, this is indeed another good news. And this motivates our exploration of PINN-based methods. So we start thinking about PINN. So PINN that integrates physical laws into neural network training by minimizing loss of the function that combines PDE residuals and the data bitting. And this approach allows for simulation of physical phenomena without traditional discrete schemes. And we believe, and it also proved itself very well, a promising tool for computational mechanics. And in practice, it's also beneficial as it automates the gradient computation. It natively handles minimization as well. So that's with PD at hand, the PD have been very successful applied in these areas, such as fracture mechanics and turbulent flow and topology optimization of wave propagation, and more recently, it's integrated into the NVIDIA Modulus platform. I'm really astonished by the fact that it is working really well, and that can create astonishing replica of this complex large-scale system. And this application demonstrates their versatility in solving physics-based problems with complex geometries and boundary conditions as well. And because of that, before we move on to liquid crystal, we start first working on solid mechanics. And this actually convinced us to work in this fascinating field. So I'm just going to introduce a little bit of it. So in concept modeling of a material, it's typical to create a well-defined the specimen and test mechanical response for a well-defined boundary condition. And this is worked on based on the ASME code or something. But however, this is often fictitious in nature because it doesn't concern about like non-locality of the material, and also expensive because it requires additional specimen, and sometimes it's misleading if not both. So therefore, uh, it's required to get it is desirable. I mean, to get material content model directly without creating another extra specimen for the given strain field and conditions, because with the aid of digital image correlation, by taking a photo of it, you can get a field of displacement as well as strains. So it can be considered as the input for the given strain field and boundary condition, and it can we are trying to get a material content model, and but if unfortunately, if only the data is considered, we've also found that physical constraints such as like objectivity, consistency, or stability can be violated, making the data or the model is completely nonsense, such as in the case like when you strain structures, the energy goes down. It doesn't make sense at all. So instead of instead of doing that, uh, we believe that the PIN can be a good choice to address this matter. So using PIN, we were able to integrate this all physics all together, like tensorial constraint are incorporated into the system with very easily. And by doing such physics constraint regression, it was possible to get solutions with unprecedented accuracy. And what is more, it does not require any model selections. So we just use a data as it is. And lastly, is robust to derivative data corruption thanks to the machine learning architecture, because this noise is inevitable no matter how good the IC system we are using. So this is the first approach for PIN. And during the working with the subject, we have figured that benefits are actually not cost-free when it comes to phase train changing material. It is because the PDE should be a variational PDE, meaning that it can be calculated out of free energy and variational principle, such as like you can see in Brocchier-Strong curve and Euler-Brenner beam problem. And they are based on the action principle. The action principle is actually a well-known, and if you have taken like the physics class 101, you have may heard of it. And this is one of the variational framework that predicts the stable state by minimizing the action functional. And in action principle, PD is obtained as a Euler-Lagrange equation by using this functional. And once it's obtained, it can be directly integrated into loss function as shown like this. The caveat is that the PDE solution is unique only when the action is convex. But as I mentioned earlier, the liquid crystal or the Landau phase transition in overall is not convex. So our question is, can PIN effectively predict the Landau phase transition and liquid crystal behaviors with given that there are three challenges? And secondly, maybe we can do it, but what are the potential advantages compared to existing numerical minimization method? Because numerical minimization method, obviously, it doesn't require any training or data, so it can be faster, but there are potential advantages of using neural network. So in order to address that matter, we are proposing this method. So the RP square, the one unique characteristic of liquid crystal is topological representation of the erector field in RP square space. This is inevitable because the molecule shape doesn't have a really orientability, meaning that minus n or plus n is equivalent. This accounts for equivalence of orientations but it still adds a complexity in modeling their behavior, particularly when the defect arise, like shown here, because there is a inactive discontinuity. And we call it disclination. I think I missed the circle here. So that's why the traceless and symmetric Q is introduced. But the problem is when you are using PIN natively, the pneumatic director and the energy. So I think N is not actually R3, but there maybe their components are, and X and then Y maybe are the real values, but it's the when there's a back propagation, there are conflict of handling the spaces. So it is not very efficient. It maybe it's possible, but it is hard to treat the queue within this network itself. So instead of doing that, we introduce a relaxed queue. I have to say, we say the queue tilde. This is the one that one tensor form, but it has a relaxed function space as a replica of Q tensors. This approach is suggested by these two papers, and this approach simplifies the representation while maintaining its symmetry and trackless properties. And this formulation inevitably increases the degree of freedom from 3 to 5. It adds a computational load only by a margin, but it greatly facilitates simplifies our search for the solution. And also, we modify the laws by incorporating action directly into the architecture to leverage the variational principle instead of using PDE. Of course, this is not new. This is very similar to the idea of discrete energy method proposed New and Tan, where he proposed using potential energy instead of PDE and argued that the improved conversions can be found rate because a higher gradient found in PDE is not present in the potential energy. The first question in mind is that whether the PINN and action PINN lead to the equivalent solution and where the functional is convex. So we take the cyclotron example here, and this is the nullity solution and the PDE, and the loads are their loads are well known. Unsurprisingly, the action-based loads gives out the solution that's equivalent to PDE, and it ensures that our framework remains consistent with established variation principles while enabling its use for efficient neural network training algorithms. However, this is not
How you can you say so the loss function is the sum of the action and the PD and the BC, the boundary conditions,
right.
and you just add them up. You don't put coefficients in front. Any
Oh, that's
weight,
true. Mhm.
right?
Yeah, right.
Okay. Okay.
Oh, yeah. So, but if it was not free again because of the nature of phase transition that from -1 to +1, and it's very sharp. And between this interface between saturated phases, the gradient phase is very high because of the system changes very abruptly. And the contrast gradient is left it underestimates other smaller side changes. So if it is left as it is, it gives out somewhat similar to gradient vanishing phenomena. So to address challenges, we have to use some other modify the architecture, and it turns out that the combination of residual block and transform networks was turned out to be working okay. And so we adopt.
Hey, Hayoung, this is Suku from UC Davis. So I had just a short follow-up to what George asked before. That you mentioned that you minimize the action as well as the PDE, or just the action and the boundary conditions, right?
Oh,
In your last,
action and the boundary condition.
yeah. So there's no PDE there, right?
No, there's no
Yeah,
PDE there.
because the action is taking care of that, right?
Right.
Yeah. Okay.
Sorry, I think that the sound is not clear enough. So when you're asking, would you please turn your volume a little bit more higher?
Oh, okay.
Yep, thank you. So we adopted this system, and yep, let me continue. So let's start with the consideration of proposed architecture, and we first looking into the energy barrier of the simple Landau Ginzburg free energy. So, and this energy is somewhat similar to one that found in phase field method. So this is our first approach. And state phi should not cross somehow the energy barrier here. And if we don't consider the gradient imbalances, the prediction earlier saturate into interior region or become overly sensitive at the interface. And it introduced a numerical instability, and it leads to saturation of trivial result like this. So in this one example, so this is how action pin and integrating simple action loads is used here. So I want to emphasize that this one uses our modified architecture, and this one is replacing the using loads as the action. But it's possible because like when you just simply add a non-convex action into the loss, it easily saturated. We just get the trivial solution as epoch goes. But if we use the architecture here, we can clearly see that the energy barrier has not been crossed. And here's another way to look into the 1D problem. So we compare how PINN and the action PINN handles the phase transitions. And this is the little more trickier because it has an unsymmetric term, making there is the one energy minima, although there are multiple inflection points. So as you can clearly see, action PINN behaves better fidelity by using action principle, enabling is captured the phase transition to be ordered and disordered states more effectively. So when you see the right figure predicted energy minima, the PDE-based solution converges into trivial solution, while the action PINN behave better, predict better than that. So it's due to the standard PINN that use PDE can identify the global minimum point among the stationary point, and the initial training point in neural network is close to 0 because of the noise as an initial guess for a stable training. So its capability of transition smoothly between state demonstrate the flexibility of our methods. Again, such differences in the prediction capabilities originated by the difference in the free energy profile. So when it's convex, there's no differences in using the PDE-based PINN or action PINN that we proposed. But when it is a non-convex, these two different architecture shows different results. We also dig in a little bit more detail by using the Lowe's landscape suggested by Lee et al. In 2018. And this visualization shows the function values across the parameters in neural network. For the PDE-based PINN, the landscape is relatively flat and less structured because it was possible because it is on the flat point among all the possible energy landscape. In contrast, the action PINN introduced a much more convex and navigatable landscape, making optimization a little bit more robust and stable. So we believe that its enhancement is one of the key reasons for this performance. And we move on to a little more practical problems like 2D. And in this case, we explore the liquid crystal behaviors by minimizing the total free energy, where phase transition and distortion energy, as well as the boundary condition problem. So taking your questions into this problem, these are the actions, and these are the L2 norm of the boundary condition, not PDE, but boundary condition as the typical loads as it is. So the computational domain here represents.
Hayoung, this is Sukho again. So just a clarification on this, on the action. So you basically incorporated the original action and you added the boundary condition part, right?
Right.
So, but typically when you solve, any variational problem, the space is constrained by the boundary conditions, right? So you're only looking for solutions in the space of functions that satisfy those boundary conditions. Right? Because otherwise you could have solutions which are outside the space, which are wrong, of course. So the minimizer that you seek could be outside and could be lower than the actual solution, right? So you typically would like to fix the boundary conditions a priori so that you're in the right space. But whereas you seem to be sort of putting it both together, kind of, right?
That's true.
And there's no Lagrange multiplier or something like here, right?
That's true. Yeah. So in practice, when you're using the when you're using PDE or other method like fine element methods, we have to use like strict constraint on the boundary for the liquid crystal or like phase transition problems, such as no matter whether it is a fine element or a finite difference or a phase field method. But in this case, it's something a little bit more intriguing because like for this case, losses are separated, right? And for the boundary condition, it had to be strictly satisfied. So I have to say we have to do a fine tuning of the parameters in order to get a solution that strictly abide by the boundary condition first. And then we are still working on the action principles. Does it clear to you?
What is the boundary condition here you're imposing? Can you just
Oh,
sort of
yeah.
point it out?
Oh, this is the can you see the black line here?
Yeah.
Yeah, we say this is we impose a homeotropic anchoring region, but technically it is a condition that it is the liquid crystal in this area is normal to the director, normal to this surface. And also for colloid, the liquid crystals are aligned the perpendicular to this the colloid. So this is very typical boundary conditions, but in fact, the liquid crystals are not the one that abide by the strict boundary condition because those kind of boundary conditions should be imposed by the anchoring energy between the interface. But to make things simpler, we just apply this boundary condition as a like Dirichlet boundary condition.
Okay. So in FEM, if one solves this in FEM, you would impose directly boundary conditions.
Right. Oh, can I continue?
Okay. Yeah.
Oh, thank you. Thank you for your question. I think that makes it a little bit more, make it clarify. Thank you. So these are we believe it was great test. And we first sold we using a PDE based PIN and also with the action PIN. We also found that both residuals are converged into zero, technically zero. So no matter what method you're using, we get a good residual values. And it is possible because the action PIN minimize the action, but it ends up have some point, a stationary point, but in that case, it also satisfies some PDEs, even though it is implicitly it is not considered. But if you consider the free energy, even though we get the solution from PDE based PIN, but their energy also stuck in zero, which meaning that the energy is on the settle rather than the global minima. So the real difference is how actually each method predicts is free energy and liquid structures. So the color here is actually denote the color here is denoting the energy profile, and you can clearly see that when this energy is combined, the typical solution that use PDE is fully saturated with zero related terms. But on the other hand, this action PIN predicts a more the lower value, but some point that are highlighted. This is physical because, as I mentioned earlier, there are textures that are discontinuous, and when it's discontinuous, there is the order that is collapsed to near zero. We call it defect, and this is physical. And we delve a little bit more on the next slide. Okay, so this is the most visual proof our method success. Comparing the ground truth and action PIN and the PDE PIN result, we can see how closely action PIN matches with the actual liquid crystal textures. It accurately resolves a nematic and isotropic regions and also captures the defect patterns. The traditional PIN struggle to replicate these results, highlighting the advantage of our action-based framework. Next, we step into 3D liquid crystal modeling. And I'm not going to talk about that much detail about its conditions.
Hayoung, can you go back to the previous plot?
Oh yeah, sure.
Like the action pin versus ground truth, still big differences, right?
That's true. When it comes to defect, yep, it's true. But their energy difference is really small compared to the
But
other.
if you look
So
at the upper right, for example, the defects are at 90 degrees off. The upper right,
right. You mean
yeah.
this one?
Yeah,
This
if you
region?
look at the picture above, yeah.
Yeah, that's true. So I think I forgot to put the energy here, but the energy difference is quite small. So we believe both are the local minima. But because the ground truth is also based on the phi element trajectory, so actually action pin has a slight higher value than this ground truth. But yeah, we are still working on it to find a better way to get the real ground truth. I think you got a great point. Did it answer your question?
Yes, thank you.
Yeah, thank you. So for a 3D, this is the texture, but it's harder to visualize. But we have two scenarios. This is a separate Saturn rings and entangled H-shaped ring. I don't know about this namings, but we adopted this naming from like expert from liquid crystal. So that's not on me. And this prediction actually showcased this intricate configuration, but you can clearly see the differences. So as George has pointed out, there is indeed differences. So you can see the red here, the red and blue. So red and blue are both the defect predicted by either the ground truth or the GPU-based optimization or the action pin. But the fact that they are not actually coinciding. So you can see there is a gap between them. But you can also figure out that their topology is quite similar, as you can see. So this is called saturated Saturn rings defect, and the right one is entangled H-shaped ring. So I have to say, this captures the subtle features that are often missed by conventional methods. So these are the case. And we also evaluate the free energy profiles in 3D textures. And projecting the bulk free energy, we can see how action pin compares to the ground truth. So you can see the energy around the defect. And overall profiles and energies and error minimize the error significantly compared to traditional methods. So and having said that, I have to say it is still slower than the optimization method or find a different method, but we were trying to find out what is the good point of using neural network. So there's one of the benefit is that it can the result can be scaled up or down very easily without further training it. So we using the transfer learning. This is actually the powerful approach improving both efficiency and accuracy. So we just try to reduce the mesh. We first tried this model with coarse grid with 25 or multiplied 25 points. And afterward, trying the length parameters into finer grid with 100 and 100 points. I have to mention that this both of these scenarios are also not not related to mesh, but it's physics itself. So layers corresponding to it remain untrainable, while finer gray layers are trainable. So allowing the model to refine prediction more seamlessly. So, and this slide shows a common baseline comparison, which is a numerical interpolations. So interpolations provide a quick estimate of a high resolution result, and it seems okay, but it often violates the tensor invariant and lacks accuracy. Let me demonstrate the rationale here. So here you can see the differences between the predicted crystal textures between the ground truths, interpolations, and action pin and transfer learning. The actual error of the interpolation is around like I forgot to put that here, but about the 10 to the minus 2. But action pin, it has a 10 to the minus 3, and it also, when the transfer learned, it also has a 10 to the minus 3. This also demonstrates how transfer learning sharpens the prediction with maintaining our efficiency. So also, if you get down to the scala of the parameter, these changes, the differences are more salient. So action pin with transfer learning here, it shows that the solution is actually refined compared to the one that is interpolated. Also, more than that, the interpolated solutions violate the tensor invariant, which leads to physically unrealistic predictions. So, for instance, the scalar of the parameter derived at point A to C, and the B is the one that interpolated, and action pin on the other hand, and we pick out the same point. And it is, of course, unphysical to have the scale of the parameter jumps from one point to the other when A to C is very smooth. So if you see the interpolated value, it just somehow the drop down to 0.3, although all the solution should be around 0.5. It is possible because we are not using S to be predicted, but S is actually deduced from our Q tilde values that is actually learned by the network. So to summarize, the transfer learning enhances accuracy, but also respect the physical laws that reduce computational effort. So it allows us a scale simulation to final resolutions without retaining from scratch. So this is our future work. So we are still working on it. So moving forward, we plan to extend the action pin to the deep ONAD framework for real-time prediction of liquid crystal textures and systematic identification of LC parameters from the observed LC texture data. So this is the example. So we just try to make the colloid moving around. Of course, the predicted energy is so not actually even close to ground truth, but we believe that we can find out the better architecture, better tuning of the architecture that models the liquid crystal. And once we've done that, we may have like better ideas. And we're also exploring the non-parametric identification of plastic material behaviors to expand our previous application of PINN that was presented in last year. Okay, to summarize, the predicting the phase transition energy, phase transition materials is critical for advancing the mechanical engineering. And secondly, the action pin incorporates action as its loss and addresses gradient vanishing found in the phase transition or gradient imbalances. And action pin predicts the relaxed states of phase transition material, and its loss landscape is more convex than residual Euler-Lagrange equations. And also, lastly, the solution fidelity can be effectively enhanced through transfer learning. And I want to give my special thanks to one of my students, who was Mr. Samuel Lee and the Dr. Ik-Soo Chung, who worked on PINN and constitutive modeling. So this is the end of my talk, and thank you for your attention, and I'm looking for your questions.
Thank you so much, Hayoung. That was a really, really nice talk. Do we have any questions from the audience? Okay, then in that case, maybe I have a question. When you said that you did not use any weights for the losses, right? That you use only one.
No. So when it comes, for example, when you're using a 2D problems, we have to use a weight on the boundary to impose boundary conditions.
Oh yeah.
So technically, we put the more weight at the beginning to make the liquid crystal textures to satisfy Dirichlet boundary condition, and we gradually relax it.
Oh, okay. I see. Okay, thank you. Because I saw that you're also using this. I thought that since you showed the picture about the gradient, I thought you were using this gradient based annealing like by Zifan one that you showed. Because I remember you showed in one of your slides.
Oh yeah, sure. So you mean probably mentioning this one, right?
Maybe before
Maybe this one.
here. Yeah,
Yeah,
this
yeah.
one. Because I thought that you were using this strategy.
Oh yeah. We tried that, and sometimes it worked, but sometimes it doesn't. So we want to make it robust, so we're just using like non-scaled value. But in this case, we use ResNet, and we combine ResNet and the transformers so it makes it somewhat working.
This architecture looks quite similar to the also I think it's called modified MLP. They also then they do this U and B and then they
Oh
and
right,
then they
right.
do this.
Hmm.
Yeah, and then you added like the skip connections, right? Okay,
Yeah.
that's quite interesting. Yeah, okay. Do you have any other questions from the audience?
Oh, sorry.
Um, yeah.
It was good talk, Hayoung. Thank you very much for coming.
Thank you. Yeah, thank you so much for your kind invitation. It was I'm very honored to give my talk in Crunch seminar.
Looking forward to the DeepONet results too.
Thank you.
Okay. Thank you so much, Hayoung. Thank you so much, everyone, for your time today. And until next Friday.
Okay, thank you so much.
Bye-bye.
Bye-bye.
Happy holidays, Hayoung.
Oh yeah, thank you so much. Happy holiday too.
Bye.